We're going to take it about an hour and a half in. So you have an hour and a half, but not right now, because usually I was building like some time because I had people who forgot to bring their calculator. So they kind of ran to Target and buy one. So it always happens, and 6 o'clock is just rush hour. So something always happens, and it's just a better thing to do the exam last.
This is such a bad question. Do you have an extra printout? I forgot to print mine out.
I'm printing out a bunch right now.
Oh.
Maybe it's Academy.
Which is actually already done, so this printer is actually
Thank you
faster
so
than I thought. And I have 4 copies, so let me put that under the stapler really quick. Or actually, let me staple this really quick and then come back.
Oh, so we're pushing. So we're getting out of time pretty quick. Yeah.
It's almost nice to have it done.
Yeah.
Because then you can sleep on that. Are we ending the exam and once we're done we leave, or?
Once you're done with the exam, you leave, or you pass it, you move, and you'll please. Okay. We kind of already talked about the properties of the atoms, and you've already looked at the shape of the orbitals. You have a, what orbital is this? P orbital, thank you. And then you have the s orbitals, you have the d orbital that looks more or less like that. Now, and essentially those orbitals are basically just the shape of the wave functions of the atoms themselves. And the short kind of explanations of things is that what we think of a chemical bond is really just a form of interference, right? So we can have 2 different kinds of interference. We can have a constructive one where the 2 wave lines up, and in which case it becomes larger. And we can also have a destructive interference where the 2 wave completely cancels each other out. And in fact, that's essentially what happens. You obviously know that there's chemical bond, but there's also a thing called the anti-bonding orbital, and it's essentially just you have 2 waves. You can either have constructive interference or you can have a destructive interference, and essentially that's going to change the probability natures of where to find the electrons. So the short terms of it is that we can have a constructive interference. So let's imagine an s orbital, like a simple s orbital, and we have 2 of them. And because they're both the same phase, so this is the nucleus, and we have the electron shell there, or the electron density, and both electron density are having the same phase. So what happens is that they're going to combine, in which case you're going to get a much bigger molecular orbital now instead of atomic orbital, which is really the combinations of these 2 wave function of, in this case, just the s orbital. You can also have an s orbital overlapping with another one, except you can also have it overlapping in the destructive interference type thing, and in which case you can have a destructive interference right here in the middle. So what happens is that when you have a destructive interference, you have one side is a positive and the other one is a negative. So when you add it up together, somewhere in between them, there's going to be a 0. And if you remember the terminology that we use, the 0 is where the probability of finding the electron is also 0, and it's also called a node. So we can have, oops, my pen stopped working really quick. Okay. So essentially the combinations of these bonding and anti-bonding orbital looks more or less like that. Oh, sorry, it should be the red one now. And one side of the nucleus, it's a bit of a lopsided circle, and I'm not drawing it exactly correctly, And now it looks like a piggy, but anyway. In any case. Now, so we have, we can have a positive and positive, in which case everything becomes a much bigger positive, or we can have a positive and negative, in which case we have now created a node. So essentially, you can have either a constructive interference or destructive interference. So if you simply look at it from this particular point of view, which one's going to have a bigger energy, or which one's going to be higher in energies, which one is going to be lower in energy? The constructive or destructive interference? Uh-oh, where are we? Sorry, I just lost our page. Oh, actually it's down here. So this one here, the destructive one, should be higher in energy, and the constructive one is lower in energy level. And yeah.
So by higher energy, you mean the electrons are higher in energy?
Yes, they are. Less stable. How about that?
Yes.
This one is more stable, and the other one's less stable. And if you want to remember, why is it this one lower in energy? Well, if you remember from our wave function, if I have a wave function that looks like this versus a wave function that looks like that, the one with the larger wavelength would be lower in energy. So this is low energy. And essentially that's exactly what happens when we have a constructive and destructive interference. That is, initially the size of our wave function is this big, but now since we have a constructive interference, the size gets bigger. So now my wavelength increases, so the energy goes down. Whereas on the other one here, remember, even though I'm drawing this as a circle, the actual wave function of the atom actually extends all the way to infinity, right? Because the wave is just a continuous thing. But now that we have a destructive interference, we literally cut access to half of the universe where this electron could go. So we literally put a boundary in between these two atoms that the electron density can only go on one side. So we're shrinking the size of the wavelength. So when the wavelength goes down, the energy goes up. So mathematically, of course, it's not going to be exactly the same as what we did with the de Broglie wavelength, because it's all about the shape and the size and everything else. But the idea remains the same, because the wavelength here gets smaller, then the energy goes up, whereas here you will literally combine the two wavelengths together to make it bigger, so the energy goes down. So kind of a more formal picture, if one were actually draw the wave function of a 1s orbital, it looks kind of like that. So when you combine it, in terms of the probability density, we can now have an extra probability density here in between the two atoms, hence it's called the bonding orbital. Whereas when we have an anti-bonding orbital, again, there's literally no electrons between them that binds these two atoms together, so we call it an anti-bonding orbital. And both do happen when these two orbitals come together. Right now we're going to start with two atoms that are exactly the same, so in this case just hydrogen, hydrogen, and as we move on to more complicated things, if we have time, we'll talk about, say, lithium and hydrogen or something like that, and see how that will look like. So instead of kind of drawing every single one of these things, we can just kind of simplify it into an energy diagram, so which is more or less looks like that. So this is called the MO diagram. Whenever you see like a stripe, and then it looks like a combinations of stuff, of two lines combining together and so on, it's usually called the MO diagram or the molecular orbital diagram. It's no longer the atomic one because now we put two atoms together, we get a molecule instead of an atom. The way to read this diagram is that if we only have two atoms, this is before, and then this is also one of the hydrogen atom before they bind, and then the one in the middle here is after. Right, so before we have one hydrogen atom, and the other one on the other side. Before we have one hydrogen atom, and when we have the wave function combined, you can have both. You will have both the bonding orbital as well as the anti-bonding orbital. And then the whole thing comes out to the same thing that we did before, which is the Hund's rule, the Pauli principle, and so on and so forth comes back in. That is, the electron will always fill the lowest energy site first. And then they will pair before they fill into the next one. So in this particular case, when two hydrogen atoms combine together, we have one here, and two. We start out with two different atomic orbitals, and they merge. They can have either constructive or destructive, and they split into two different atomic or molecular orbitals. And yeah.
I'm sure you're getting into this, but does antibonding or bonding happen because of the spin of the electrons?
Yes and no. So there's a spin here that's kind of implied, but what it is that the spin of the electron can be easily switched. Okay. So what happens is that it's just if the spin is both spin up, right? So if they both spin up, there's no reactions, there's no bonding could happen. They need to flip the other way around in order for the two things to merge. But it will happen eventually if you just kind of leave them alone, because it's easy. It's the switching between spin up and spin down is fairly low in energy, so they switch around. So essentially that's about it. And the reason why, for example, if we look at hydrogen atom or hydrogen, they don't exist as an atom, but rather they exist as a diatomic molecule of H2, because H2 is more stable than a regular hydrogen atom. And we know that it's more stable because the energy level of this combined orbital is lower. So initially the energy of the electron is high, and after they combine together, they become more stable. So the energy is lower, so they're more stable. And in the meantime, when we have this reaction happen, there's an energy difference between these two states. So essentially the energy that we get from a chemical reaction is just the energy that we get from these two states. It can either come out as light or so on, or it can also come out as as heat. Okay. So far so good? Yeah? Now the idea is pretty straightforward. It's just constructive interference, we get a bonding orbital, and we can also have an anti-bonding orbital when it undergoes a destructive interference. But it seems simple, but it's quite powerful because we can actually start to predict why some atoms are more stable than others and some are not. So for example, if we look at H2 molecule, we look at the periodic table, each of the hydrogen have a single electron on them, and when they combine together, the electron will fall down, and one can see now that the electrons are lower in energy, so in this case, H2 is stable. And we can also predict another property, that is, you can see that this is initially unpaired, but now, when it comes out together, H2 molecules is also now paired, so this becomes a diamagnetic molecule. So just immediately by drawing the wave function before and after, just kind of constructive interference, destructive interference, we can immediately see that H2 is more stable than individual hydrogen atom, and it's also going to be diamagnetic instead of paramagnetic. We can also predict, for example, what happens if you have an H2 minus. Well, let's just say we have an H minus as well as an H0, so it's neutral. If hydrogen is neutral, you only have one electron. If you have if you have H minus, means you have one extra electron. So what happens is that when the electron can join together, you get, in the end, an energy diagram that looks like this. That is, same rule as before. We fill in the bottom first. We have 3 electrons. So 1, 2, 3, last one at the top. Then we can now see that this new atom, if it exists, it's going to be paramagnetic. And it's going to be somewhat less stable than H2. Because now, instead of having it in the bonding orbital where it's stable, it's in the antibonding orbital, and it's literally higher in energy than the orbital. So most likely what happens is that when you have this, the antibonding orbital is going to come off easier. So the last electron here is not going to be that stable. And just kind of finishing off this whole thing, we can also look at helium-2. So is He2, a diatomic helium atom, stable or not stable? And it's the same game too. That is, if we have helium atom, helium is, each helium atom have 2 electrons. So when you have 2 of these, I need to change my pen, I think. And we have 4 electrons now in total, so when we fill in the new molecular orbital diagram, it's 1, 2, 3, 4. And we can see that, oh, there's actually a lot more here. So one would expect that helium-2 is not as stable. So far, we're kind of just looking at it based on the diagram itself. We can also do some bit of calculation, and the stability of the atoms can be described what they call the bonding orbital, bond order, excuse me. And the bond order is pretty straightforward. Is equals to 1/2 times the number of electrons in the bonding orbital minus the number of electrons in the antibonding orbitals. And I think there's little equations on the top as well. So I'm just going to swipe to the side here. So what happens if we calculate the bond order of helium-2? Well, the bond order of helium-2 is going to be equals to 1/2. And how many electron is in the bonding orbital? Well, this is our bonding orbital. So we have 2 electrons in the bonding orbital. And we also have 2 electrons in the antibonding. So this is bonding and antibonding. 2 minus 2, so it's 1/2 times 0. So the bond order is 0. So it's not a stable molecule because it would not make any bond because the bond order is equal to 2. So it's just kind of a bit more of a formulaic way to write it down. Right. And it's just 2 minus 2 times half, which is just a 0. We can also look at why hydrogen atom is more stable, because if we look at the hydrogen atom here, when we calculate the bond order, it's just going to be equal to 1/2. So how many electrons in the bonding orbital? Well, we have 2, and we have none in the antibonding orbital. So in this case, the number of bonds is equal to 1 for H2 atom. Have you guys seen Lewis diagram? Maybe a while ago. In essence, what you calculated in the bond order is going to be exactly the same number of bonds that you'll find in the Lewis diagram as well. We'll cover that as well later, but here are kind of a more of the basics of it. A more detailed version than just the Lewis diagram, instead of just assuming they will make a bond. So far we kind of look at their diamagnetic property, their paramagnetic property, as well as the bond order. And the thing that you want to remember is that the bigger the bond order, the more stable the molecules are, because it simply means that a lot of its molecules are going to be in the bonding orbital, in which case it's lower in energy, therefore it's much more stable. Yeah, more stable.
So H2 minus is 25, right?
Yeah, so in this case, H2 minus, the bond order is 1/2. Yeah. So that's it so far. And of course, we just started talking about the simplest possible electrons, simplest possible wave function, which is just the s orbital. So what happens when we start to extend this whole thing into much bigger orbitals? That's when things get a little bit more complicated. So we kind of have to put in a little bit of extra definitions in our repertoire of stuff. The first one, I want to define, there's two different kinds of bond. There's the sigma bond, so sigma bond, as well as the pi bond. So if you have a bond, you put just a sigma and a pi on its own. And if you have an anti-bonding, to refer to this thing, we're going to write it down as sigma star, or pi star. So whenever you see a star on the top of it, it tells you that it's an anti-bonding. It's just, it's a lot more compact, that's all. It's just some vernacular stuff. Most of the time, the sigma bond is stronger, most of the time, and the pi bond is usually a bit weaker. So the best way to understand which one is a sigma bond, which one is a pi bond, is just basically try to draw it. So here, this is what I like to call a sigma bond is a direct overlap. So in this case, if I have two orbitals that looks like this, so this is an s orbital. This is a sigma between s and s orbital, for example. So if I were to write down this is sigma between s and s. We can also have a sigma bond between s and p. We can also have a sigma bond between p and p orbital. Right? So these are the shape of the bonding orbital. So if we were to have to draw the anti-bonding orbital between the two s orbitals, then it would look more or less like this. Obviously, what is that? Okay, so I'm going to draw the easy way to draw it, which is if you have an anti-bonding orbital between two s orbital, then it looks like that. It just simply indicates that one is one way, the other is the opposite way. But in reality, of course, when these two things combine, it's actually going to kind of look more like that. But it looks kind of like two blob. It's almost like a p orbital, but not really. Like a misshapen p orbital. But obviously this is hard to draw, so this is way sufficient, and majority of the time you'll see the drawing, it is done by hand to look like that, and so unless you have like a good computer graphic, it's just easier to show it that way. So if you have a sigma anti-bonding between s and p, well, you can just have a drawing that looks more or less like that, right? So that's a sigma bonding, sigma anti-bonding between s and p. So now it overlaps directly, but one of them is an anti-bonding. They're overlapping on the opposite face, and of course the actual shape will look closer to something like that, which is kind of hard to draw, so we don't have to worry about it too much. And the last one, if we have a sigma bond between two p orbitals, p and p, sigma star p and p, we have something that look like that. And it's just just an antibonding orbital. So they overlap in the opposite phase. It's pretty clear-ish. I can kind of give you guys the definitions of exactly what is a sigma bond, but in the end of the day, you just have to draw it and you'll know what it is. It's much easier to understand it based on the picture and what it looks like. So, these are the pi bonds that we have. So, of course, this is usually at least for the purpose of our class, I'm just going to write it down as a pi P and P. This is a pi bond between P and D, and this is a pi bond between D and D orbital. So, how would you draw? Rachel, can you draw for me a P and P orbital antibonding orbital? Pi antibonding orbital between a P orbital and a P orbital. Anthony, can you draw the next one, please? The antibonding orbital between a P and a D orbital. Yeah, just on the board, and we'll just kind of compare it. And I guess Angel, because you're closer, can you draw the last pi antibonding orbital between D and D? Yeah. That's a sigma. Pi. Yep, that looks right.
Oh, okay.
Yeah. Yeah. Not quite. That's a bonding orbital. Because you can see that the darker shaded one overlaps exactly with the darker shaded one. So it means this phase is the same, so you have a bonding orbital. They overlap in the opposite phase. Yeah. Yeah. Yep, that's it. Angel. Yeah. Oh, hold on. No, not quite. No, that's a constructive interference that you're drawing. Oh, sorry. I didn't get the chance to see yours. I was talking about English. That's a constructive interference. Because the phase, this and this is the same phase, this one and that one is also the same phase. So they'll combine together. Right. So they have to be opposite phase. No, that was the same as before. This and this one is the same phase. So what happens is that because they're the same, they will Yep. Yep. So essentially, so we'll just kind of draw that at the end as well. So you have one of them is shaded on the top and on the bottom. So these are the anti-bonding orbital. And I put a star on the top to denote anti-bonding orbital. And the same with this one too. So this is a pi anti-bonding orbital between two d orbitals. Right, so they overlap, these two overlap constructively or destructively. This is a more cartoony picture of it. I believe your textbook have it, or they may not. But essentially, the actual shape of the orbitals can be quite complicated. That is, if we were to look at the pi PNP bonding orbital, essentially their actual shape looks more or less like that. So that's the actual shape of this particular orbital, because the two lobes here, the two p lobes, are going to overlap together to make a much bigger thing. Whereas when we look at the anti-bonding orbital, the actual shape in the end is going to look kind of weird, because we now have, so if I were to draw this, sorry, I have to draw this one a bit more carefully. So the actual shape of this one, we have two nucleus, and then we have a node in between them, and it would actually kind of look like that. So this is the cartoon picture that we have, the actual shape of the orbital. Remember, the middle part here will cancel out, so there's nothing there, and it's kind of weirdly flipped that way. And you can see that these are going to be even more complicated and so on, and I'm not going to try to attempt to draw them. They're quite annoyingly complicated to draw. Like this one would look like that, which is kind of weird too. So the shape could, once you actually draw the shape and do things like that, they merge, so it looks kind of funky. So might as well stick with the original shape that we know, because in the end of the day, it still communicate about the same level of information anyway. They're just kind of harder to draw, which we don't give too much about. So let's see, who did I not call yet? Paul, what kind of orbital is the one on the bottom here? Okay. Okay, so it's a sigma bonding orbital, so it's going to be a sigma. Oh, my pen is dead. Okay. I need to use my touch then. Right, so this is going to be a sigma between D and D orbital. And we know it's a sigma bond because the orbitals are overlapping directly. And we have two d orbitals. And the one on the top here is going to be a sigma bond between a p orbital as well as a d orbital. So the naming system, hopefully it's kind of fairly straightforward, right? So the simplest possible bond that two s orbital can make is essentially a sigma bond, and the first the pi bond can only be made initially by pi orbital, and obviously we can extend the type of bonds once we get to more complicated and transition metals especially. So we can have two d orbitals that kind of overlaps like a sandwich. So if you can imagine, there's two d orbitals right on top of one another. So it's just, I'm trying to draw it, but I'm not sure if I can. it's supposed to look like a sandwich, so you have two d orbital right side by side to one another, and if their lobes are overlapping exactly right, you have a sigma bond, you have a pi bond. How would you call this particular bond? What? No. This is a sigma bond, this is a pi bond, S, P, D orbital. It's going to be a delta bond. Or I should say a small delta. But anyway, the naming is not very imaginative. Anyway, so we can see a bunch of other bonds like those ones, but we're going to limit ourselves predominantly for the s orbitals as well as the sigma bond as well as the pi bond, because those are the most common one that we'll see, because in the end of the day we're all carbon molecules, so carbon molecules only do either a pi bond or a sigma bond. Now suppose now we're going to extend ourselves with atoms that actually have an s orbital. So in this case, let's look at a simple O2 molecule. So we have O2 molecule. The MO diagram, as you can see now, is much more complicated. So I'm not going to look at the s orbitals at all. I'm not going to look at the one s orbital. Instead, I'm just going to look at the two s orbital, because the bonding only happens on the most outer shell instead of the inner one. How many valence electron does each oxygen have? So we're going to try to draw the diagram in this case. You guys have a, might as well pass you guys the table right now. It's going to be an example. It does have 6 valence electrons each. So each of the oxygen atoms have 6 valence electron, and if we were to do the regular ground electronic state configuration, we have, the 1s2, 2s2, 2s2, and then 2p4. So it looks more or less like that, right? So 1s2, 2s2, and 2p4. Same with the one on the next one. We have 2s2 and 2p4. So that's how we get 6 valence electrons from our atom. The 1s, we don't really care about it, because when you have a chemical bond, only the outermost shell actually interacts, because the 1s is smaller and buried inside. Some textbooks actually show both the s orbitals, the 1s orbitals and the p orbitals, n equals to 1 and n equals to 2 interacting, but in the end of the day, only n equals to 2 is actually interacting. So what is the resulting molecular orbital that comes out of this? I want you to look at this one here. So the lowest possible energy state is the interaction between the two s orbitals. So this is going to be a sigma bonded between s and s orbital. Then we're going to have a sigma antibody between the two s orbitals. Then we're going to have a sigma to p pi antibody and sigma antibody. So the energy level is going to differ. So when we fill it out, we have 12 electrons in total, 12 valence electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so we have 12 electrons. So when they combine, we still have exactly the same number of electrons. So exercise. What is the bonding orbital? Bond order, of oxygen molecules that we have here. What is the bond order? 2. Thank you. And we have to count the number of bonding orbital first. So 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 bonding orbital minus, is a different color. We have 1, 2, 3, 4 anti-bonding orbital. So 8 minus 4 is 2, 8 minus 4 is 4, divided by 2, and it's going to be equal to 2. And if you remember your Lewis diagram, later on we're going to see this. The Lewis diagrams of oxygen is going to look like that. That shows that the oxygen has a couple bonds as well. So the 8 goes, the yellow goes to the 8, and the green highlight goes to the 4. So far, this is a one. There's an important one that does occasionally show up. Once you go beyond oxygen, so when you go to nitrogen, this too is going to flip. That is, instead of the sigma bond being lower in energy, when you have nitrogen, the sigma bond is actually going to be slightly higher in energy compared to the pi bond. Before we go, the bond order is 2, and I'm still using the other color, and you can see that these 2 electrons are unpaired, so oxygen molecule is going to be a diamagnetic molecule. Paramagnetic, sorry, yes. If there's any unpaired electron, it's going to be paramagnetic. So any unpaired electron, like that one, they're going to be considered paramagnetic. Now this is the next one for the nitrogen N2 molecule. And if you look at the nitrogen molecule, each of them should have 5 valence electrons. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And what I want you to notice here is, again, the sigma bond is actually slightly higher in energy compared to the pi bond. The energy levels switch between N2 and O2. And when we fill it in, we have 10 in total. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, so that's a completed MO diagram. So let me zoom out a bit. So when we calculate the bond order, it's going to be equal to 1 over 2 times 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons in the bonding orbital, and then we have to subtract it with 2 electrons in the anti-bonding orbital. So in the end, we have a bond order of 1 over 2 times 6, or equals to 3. And one can also see that all of the electrons here at the resulting molecule is all paired, so the magnetism is going to be a diamagnetic molecule. Right. So same thing, Hund's rule, Pauli's principle comes back in. We just fill it in all the way from the bottom up to the top. Now, again, the difference is that, again, between the oxygen and the nitrogen molecule is the sigma bond between the p orbitals, and this bonding here is flipped between nitrogen and oxygen. It's a bit of a memorization that one has to do, unfortunately, but I do want you guys to note that as well. And the last one here is that I kind of want to just kind of go back in and fill in the energy diagrams on each of these sigma 2s, the sigma. So you can see that there's a bunch of notation here, like sigma 2s, sigma star 2s, pi x, pi y, and so on. I want to draw all of the diagram and what the actual order looks like. So we can have a sigma bond between 2s orbitals. So it's just a regular sigma bond between 2s. We can draw it that way. We also have a sigma anti-bonding, and it just looks like that. Right, so that was the shape of the orbital there. Right. S orbital, sigma bond antibonding orbital between the two S orbitals. And as we go up to the sigma bond between two p orbitals, it's going to be in this way. Sorry, it's a bit hard to draw, but do draw them in this particular orientation, because that's the correct way to go. Sorry? Yeah, that's fine. And I notice here I made a mistake. There shouldn't be any anti-bonding sign there, so you can scratch it off. The anti-bonding orbital is higher in energy, so I put an extra exteric there. So we can also have a pi bond between the x orbitals. So I'm going to draw this y. Right. We can also have a pi bond between the y in the y direction. So, and then of course each of these are the center of the atom, and we can have a pi anti-bonding between the y and the x. So it's kind of the one of the one that you've already drawn. As long as they're opposite shading, I don't mind whichever is shaded on the as long as the shading is opposite, it doesn't really matter. And the last one, we can also have a pi, a sigma anti-bonding orbitals between the two p orbitals. So, in the end, those are the shape of all the orbitals that we have. Now, we're kind of so far putting all of them disjointed, but in fact they all originate from the same atom. So we're going to do one last drawing that's a little bit complicated, and instead of drawing it on the monitor here, because I just don't have as much control, I'm going to try to draw it on the board. I'm going to try to draw where the sigma, where the pi bonds, the bonding on the p orbital, and how they orient themselves. And I'm not going to draw the s orbitals because this is going to make things even more complicated. So we have the lowest possible energy state between the two pi, the bonding between the two orbitals is the sigma bonding orbital. So I'm just going to draw all the bonding orbitals. So one of them looks like this, and the dot in the middle is the center of the atom. And this is the N, which is the bonding orbital. We can have a pi bond between the two p orbitals. One of them is pointing outward. I think I call it the x direction, it really doesn't matter. And we also have different colors. I do have different colors. One pi bonding orbital is sticking outward and into the board. So essentially, these are all the three bonds here that we drew. Actually, just the bottom three, 1, 1, 2, 3. But everything now is connected together. And I don't have the blue. But technically, there is one last one, which is the s orbital. So far, my point is that so far we've been drawing them as if they're disjointed, but I would just want you to remember that all of them happen to the same atom, and all of these orbitals occurs all at the same time. In the other way, kind of, if we try to overlap all of them, it looks like that. And I do believe that we have a slightly better picture of what it actually looked like in the end. Right? So if we look at the nitrogen bonding, which have all of them bonded together, it's essentially that drawing here, but it's more computer generated stuff. They're not including the s orbital bonding here, but that's alright, because it's hard to see. Anyway, that's how all the atoms combine themselves and make a bond. Any questions so far? Mostly just drawing, mostly just understanding that if you have an anti-bonding orbital, it's higher in energy and so on. Again, the one that I want you to memorize for now is that for oxygen, so if you have, if you look at your periodic table, row number 2, we have oxygen, fluorine, and I forgot what the last one, I think it's neon, and then we have nitrogen, carbon, beryllium, and I don't remember, B, boron, and then beryllium and lithium, right? So when you have a diatomic molecule, there's a bit of a bridge, if you like, between the nitrogen, oxygen, and so on. So if you have the oxygen or fluorine, a diatomic oxygen or diatomic fluorine, the energy level diagram is going to look symmetrical like this. Whereas if you have Li2, Be2, B2, C2, N2, the energy diagram is going to be lopsided. It's not going to be symmetrical, that is. Right, so that's the one that I want you to know about. And the dividing line is the nitrogen line.
Neon too.
Yeah, right. So, oh, here. They're flipped.
Oh, they're flipped.
They're flipped. So this is the way that they flip is that this is the sigma PNP, and this is the pi PNP 2. Whereas here there's a sigma PNP, and then there's the pi PNP. They're flipped. But the antibonding orbital remains the same. It has a lot to do with the electronegativity of the atoms, and it's just once you reach the oxygen side, it flips. That is, oxygen and fluorine have a lot more high electronegativity than all of these on the left. Yes, it's your left too. Because they have a lot more electronegativity, the atoms are actually a little bit closer together between the O and the F. So O2 and F2 is when they bond, they're a little bit closer. So what happens is that there's a little bit more overlap between the p orbitals compared to these other atoms. So because there's a bit more overlap there, the p orbital is a bit more. The sigma bond is a bit more stable, but it's just a bit more detailed. So. And of course you can also get a few information about them. That is, if you have nitrogen gas, this is N2, you're going to find that they're diamagnetic, and if you have oxygen gas, they're paramagnetic, and if you have F2 gas, they're going to be diamagnetic again. And then you can do the bond order and so on and so forth. kind of want, yeah, the next one is Lewis diagram. But anyway, before we go there though, this is also the last one that I want you to memorize. If your atom have a single bond, there always going to be a sigma bond. If you have a double bond, it's 1 sigma bond, 1 pi bond. And if you have a triple bond, it's 1 sigma bond and 2 pi bond. This is not right, but unfortunately, if you are being tested on stuff, these are the kinds of things that people ask. Then they're incorrect because you have bonding, anti-bonding, they all happen all jumbled up together. But unfortunately, I don't want you to memorize it for the purpose of taking a test that is not you're going to use. Yeah, it's not true all the time. In fact, you can have a single bond made entirely of pi bonds, and you can have a double bond without any sigma bonds whatsoever. So, yeah, whatever. It's all about how the atoms actually align from one to the other. We can also look at. I'm going to kind of veer off a bit here. I'm adding essentially an extra stuff. So far we've been talking about diatomic molecules, so we're talking about O2, N2, you can do F2 as well. Essentially all the atoms are exactly the same. So that's why when we draw the MO diagram, this is where we started, right? We have 3 p orbitals, and we also have the s orbital, so this is 2p and 2s. And you can see that when we drew them, the energy level between the two things are exactly the same. Because, you know, nitrogen and nitrogen, they both have the same valence, Z effective and so on, so the energy level is exactly the same. But, when you're actually looking at these, heterogeneous atoms, or at least we're going to stick to diatomic for now, because they're simplest. We can also look at things like HF, for example. So, so this is the energy of the hydrogen atom, and if you look at the hydrogen atom, there's only 1 electron, and the ground electronic state is going to be E equals to negative 13.6, Z effective squared over N squared, because N equals to 1, Z effective is 1, so this first energy level is negative 13.6 eV for hydrogen atom. So you can use your Z effective tables and so on to actually calculate these things. But I thought I have it on my phone. I thought I'd take a snapshot of it. But when you look at, say, fluorine atom, we can actually try to calculate this whole thing. Yeah, why not? We can look at fluorine and we can look at the Z effective table. Yeah, why not? Why not? Let's do this because it's going to be useful for the exam anyway. If you look at fluorines, some of the values of the Z effective of fluorines is that for the one, I'm not going to look at the 1s orbital, I'm going to look at the 2s orbital. The Z effective for fluorine is 5.128, and the Z effective of the 2p orbital is 5.10, for example. We can use the same equation, the negative 13.6 electron volt, and so on, to actually calculate where the energy level is for the 2p orbitals for fluorine, as well as the 2s. So this is 5.10
and 1 to 8, this is 5.10. So when we calculate the energy diagram, or the energy of this particular quantum number, it's negative 13.6 eV times the z factor squared is 5.12 to the power 2 divided by n squared. In this case, it's 2 to the power 2. So if you do this calculation, you get the given, for example, 5.12 times 5.28 divided by 4 times 30.6. That's huge. This is going to be negative 89.4077. So this is the energy of the 2s orbital. And when we look at the energy of the 2p orbital, this is going to be 2p is going to be negative 88.4. Right? That must be because energy equals.
So the energy diagram is no longer symmetrical
Between 1 and the other. And instead we have
a huge energy barrier between one to the other. So one of them, the 2s of the f orbital, is going to be at negative 89.4, and then we also have the 2p orbital is way down here at negative 88.4. So that's the energy of the atoms there. And fluorine have 7 valence electrons, and more looks like, oh, sorry, I'm missing one more. So you can see now the bonding between these two atoms is going to be much more complicated, because the bond is going to be more or less like that. And actually, we have one over there, one over there. So we can have a sigma bond between the s and the s. So this is a sigma between s and s. We can have a sigma between s and p. And then we have a non-bonding orbital. This is a non-bonding orbitals, and then we have, so 1, 2, 3, 4. I think I'm just making this more complicated. But essentially, my point is that once your energy diagram is no longer exactly the same between the two things, the bonding becomes super weird. So in this case, it's completely lopsided. And you also have an orbital here that is, I hope you kind of notice that I'm kind of putting these two exactly lined up. You can also have things that are called non-bonding orbitals. Mostly that happens when you have heterogeneous atoms binding together. Mostly that's because the atom doesn't overlap nicely, and it's something that you kind of have to study and be more careful. So for example, the lowest energy diagram possible is just the 2s orbital combining together, so a sigma bond between the s and the s. And the second lowest energy level possible is a sigma bond between the s orbital and the p orbital. Right, that's why I'm putting a line from the p orbital down to make the s orbital down. But the non-bonding orbital here is that this is our s orbital from the hydrogen atom. It doesn't really overlap at all with the p orbital. It's not overlapping nicely. So this, if you want to think about it, this one is antibonding, this one is bonding orbital, so it's not quite right, and therefore they don't actually make a bond, and hence it's called the non-bonding orbital. And then we have things that are opposite. That is, we have now the sigma antibonding orbital as well as the sigma antibonding orbital between the S and the P. So here you have the non-bonding orbital, which more or less looks like that. So it's confused because it really doesn't do anything. Oh, I'm trying to draw this properly. It's hard to draw, but anyway. We're not going to touch into things that look like this because they're too complicated. And if you are going, most of you guys are not chemistry, right? No. Yeah. So if you're chemistry, this is like you're going to study an actual semester or a quarter studying how to draw this and what other rules assigned to it and so on.
What do you mean by chemistry?
If you're like a chemistry major, you're trying to get a chemistry degree, you can have like this is called advanced inorganic and so on. But anyway, you'll learn how to draw diagrams that looks like this. But there's one last one here that I want to mention. My point, the first point is that one, they're lopsided if it's not same atom, and in which case you have weird looking stuff. And number two is that sometimes if the energy diagram, the difference between the energy between the two atoms of two atom too large, you won't get a chemical reaction. Instead, you have a redox reaction. So you can see that this is negative 89 and so on. But you can imagine if I were to change this atom to something else, even larger, for example, this might be one of the energy diagram, and the other one could be way down here, for example. Right. So let's just say we have an atom that looks like that. That the energy diagram, the energy difference between the two atoms is so big. So what happens, instead of making a chemical bond, this electron is just going to fall in. So now, for example, you might have a lithium plus and then a Cl minus. Then you have an ionic molecule because the electron just, the energy difference is too large. It doesn't really get shared, and instead it just kind of falls right there. So the energy difference is too large, you get ionic molecules instead. Get ionic molecules. And usually you can, rather than using this kind of En and so on, you can actually use the electronegativity scale to make a prediction whether something is ionic, whether something is actually making covalent bond. So for example, I usually teach my other classes that if you have a metal and non-metal, you'll realize that the non-metal have a really high electronegativity, and then the metal essentially have zero electronegativity. So in this case, if you have a metal and non-metal, they're going to be ionic. Whereas if you have non-metal and you have another non-metal atom, then you're going to have a covalent bond. That's because the electronegativity is more or less about the same, and what happens is that it simply means that the energy diagram or the energy of the electron are similar enough between one to the other. Anyway, so this is about 7:30-ish. How long is that class? 4 hours? I can keep going. So let's take a tiny bit of break. Let's take a bit of a break, and when we come back in, we'll do a little bit of Lewis diagrams and so on, just a tiny bit to get started, and then we're going to take a bit more break and then prep for the actual exam. Right, the exam